The sum of an infinite geometric sequence. Let's take the formula Sn. So sum of infinite terms of the geometric sequence can be written as a1 first term minus a1r, second term with power rn divided by 1 minus r. So this is the sum formula. So as you have noticed in the previous lecture, for example, so this is the sum Sn is equal to a1 minus a1 r power n over 1 minus r. So here r is less than 1. So this is the general sum formula. Sn is equal to a1 minus a1 r power n over 1 minus r. And the sum of nth term, the general form of the nth term is an is equal to a1 into r power n minus 1. Now we are interested to find the sum of an infinite geometric sequence. So let's take the formula. So this is the formula to sum up n terms of the geometric sequence. We rewrite the right hand side by applying the property. So a minus b over c can be written as a over c minus b over c. Thus we obtain Sn is equal to a1 over 1 minus r minus a1 r power n over 1 minus r. It means in the numerator there are two terms and we can split these two terms as a1 over 1 minus r minus a1 r power n over 1 minus r. Now let's examine the behavior of r power n for absolute value of r less than 1, that is for r lies between minus 1 and 1. For example, suppose that r is equal to 1 by 2. Then r square is equal to 1 by 2 whole square 1 by 4 and r cube is equal to 1 by 2 cube is equal to 1 by 8 and r power 4 is equal to 1 by 2 power 4 is equal to 1 over 16. R power 5 is equal to 1 by 2 power 5 is equal to 1 over 32 and so on. We can make 1 by 2 power n as close to 0 as we please by choosing sufficiently large values of n. In general, for value of r such that absolute value of r less than 1, the expression r power n approaches 0 as n gets larger and larger. Therefore, the fraction a1 r power n over 1 minus r, so this is a1 r power n, the second term, a1 r power n over 1 minus r in equation 1, okay, approaches 0 as n increases. So we say that the sum of the infinite geometric sequence is given by S infinite is equal to a1 over 1 minus r, r absolute value less than 1. So what is the essential condition? Essential condition is that the common ratio must be less than 1. So if the common ratio less than 1, then this sum of nth term formula will be modified. How we can modify it? First, we can write in as a sum of two terms and then we will observe the behavior of this second term. For example, if common ratio less than 1, that is for r lies between minus 1 and 1. For example, suppose that the value of r is equal to 1 by 2. So then r square is equal to 1 by 4, which is less than 1 by 2. And r cube is 1 by 8, which is less than 1 by 4 and 1 by 2. Similarly, r4 is 1 by 16, which is less than r cube, r square, and r1. So if you observe that the coming terms are becoming lesser than the existing terms, and so on, we can make 1 by 2 power n as close to 0 as we please by choosing sufficiently large values. So it means if we increase the number of n, so this resulting terms are in decreasing and the value is so thus we obtain Sn is equal to a1 over 1 minus r. It means we have split this formula as a sum of two terms. Okay, so if we observe that the coming terms are decreasing and lesser than the existing terms. So that is why we can skip this second term, and if we skip this second term, we will have a S infinite is equal to a1 over 1 minus r. So here is the formula, so which is the modified form of the sum of the nth term of the geometric sequence. So if you remember, we studied this uh, this one, sum of geometric sequence. So sum of geometric sequence, so if the terms are finite, that is countable, that we know that there are 100 terms, 200 terms, or 50 terms, we will use this formula. Sn is equal to a1 r power n minus a1 over r minus 1, and r is not equal to 1. Okay, so but if the terms are infinite many terms, then many terms, and the second condition is that r is less than 1 or lies between minus 1 and 1, so then we will use a different formula. So what is the formula? Formula is S infinite is equal to a1 over 1 minus r, where absolute value of r less than 1. Here is the example. So find the sum of the infinite geometric sequence. So this is a geometric sequence. How we can verify that this is the geometric sequence? So the common ratio of this geometric sequence is 1 by 2. So if we multiply 1 with 1 by 2, we will have 1 by 2, and multiply this second term with 1 by 2, we have 1 by 4, and multiply this third term with 1 by 2, we will have 1 by 8, and so on. Okay, so that's why we can say that this is a geometric sequence. Okay, so what is the first term? First term is a1 is equal to 1. What is the common ratio? Is r is equal to 1 by 2. And we obtain the infinite sum of the infinite terms. S infinite is equal to a1 over 1 minus r. So here we need only two things, the first term and common ratio. And the common ratio must be less than 1. So here is common ratio is 1 by 2. So it is less than 1. So that is why we can use S infinite is equal to 1 over a minus 1 by r. So 1 minus half is half. 1 over 1 minus half is equal to 2. It means, so if we add so many terms as we think or we can, the sum must be 2, and it cannot increase by 2. So that is very interesting that we can add even infinite many terms, and the sum of infinite many terms will be 2. When we state that S infinite is equal to 2 in example 7, we mean that as we add more and more terms, the sum approaches 2. Observe what happens when we calculate the sum up to 5 terms. First term 1, sum of first two terms 1 plus 1 by 2, so it is 1 and a half. Sum of first three terms 1 plus 1 by 2 plus 1 by 4, 1 and 3 by 4. Sum of first four terms 1 plus 1 by 2 plus 1 by 4 plus 1 by, so 1 and 7 by 8. Sum of first five terms, so it's 1, 1 by 2, 1 by 8, so on. Let r is equal to 3, r square is equal to 3 square, r cube is equal to 3 cube, so 9, 27, 81, 243. And if r is equal to minus 2, so then r square 4 minus 8, 16 minus 32. So if r is equal to 1, then Sn is equal to Na1, and as n increases without bound, Sn also increases without bound. If r is equal to minus 1, then Sn will be either A1 or 0. Therefore, we say that the sum of any infinite geometric sequence where r greater than or equal to 1 does not exist. So this is the point to be noted, that the sum of any infinite geometric sequence with r greater than or equal to 1 does not exist. Okay. So we can only perform or add the sum, or we can get the sum of the geometric sequence if the value of r is less than 1 or lies between minus 1 and 1. But if the value of r is greater than 1 or equal to 1, we cannot do the sum of infinite geometric sequence. So the sum of infinite geometric sequence does not exist if common ratio is greater than or equal to 1. We can only find the sum of infinite geometric sequence if the common ratio lies between minus 1 and 1. Okay, next is repeating decimals as sum of infinite geometric sequence. So in section previously we defined rational numbers to be numbers that have either a terminating or a repeating decimal representation. Rational numbers are the numbers that have either a terminating or a repeating decimal representation. For example, 2.23. So decimals after point are only 2. So we can count that there are two decimal numbers. Okay, again, rational numbers are the numbers that have either a terminating or a repeating decimal representations. Okay, so 0.147 is terminating. Okay, 0.3 bar is repeating. So we can write as 0.33333, so on. Similarly, 0.14 bar is repeating. We can write it 0.14141414, so on. Similarly, 0.56 bar is repeating. We can write it 56565656 are rational numbers. Remember that 0.3 bar means 0.3333, so on. Place values. Value provides the basis for changing terminating decimals such as 2.23 and 0.147 to a over b. Form where a and b are integers and b is not equal to 0. So 2.23 is equal to 223 over 100 and 0.147 can be written as 147 over 1000. However, changing repeating decimals to a over b form require a different technique, and our work with sums of infinite geometric sequence provides the basis for one such approach. Consider the following example. So change 0.14 absolute to A over B form where A and B are integers and B is not equal to 0. The repeating decimal 0.14 bar can be written as the indicated sum of an infinite geometric sequence with first term 0.14 and common ratio 0.01. For example, we can write this, okay, the repeating decimal can be written as the indicated sum of an infinite geometric sequence. So this is another advantageous property that the repeating decimal can be written as the indicated sum of an infinite geometric sequence, okay, with first term 0.14 and common ratio 0.01. So how we can write 0.14 plus 0.0014, okay, plus 0.00014. So just observe that here we have put two zeros, and in the next term we will put four zeros, and in next term we put six zeros, then eight zeros. So in this way we can write all the terms. Using S infinite is equal to A1 over 1 minus R, we obtain. So what is R here? So common ratio is 0.01. So 1 minus 0.01, and this first term is 0.14 over 0.14 over 0.99. So this can be written as 14 over 99. It means this 0.14 can be written as 14 over 99. Okay, if the repeating block of digits does not begin immediately after the decimal point, as in 0.56, we can make an adjustment in the technique we use. Okay, so how we can proceed with change 0.56 bar to A divided by B form where A and B are integers and B is not equal to 0. The repeating decimal 0.56 bar can be written as 0.5 plus 0.06 plus 0.006 plus 0.0006, so on, where 0.06 plus 0.006 is the indicated sum of the infinite geometric sequence, with the first term is 0.06 and the common ratio is 0.1. Therefore, S infinite can be written as 0.06 divided by 1 over divided by 1 minus 0.1 because the common ratio is 0.1. And if we simplify this, we will get 0.06 over 0.9, or even we can write it 6 over 90 or 1 over 15. Now we can add 0.5 and 1 over 15, and we will get this 0.5 plus 1 over 15 equal to 17 over 30. So in this way, we can even write this uh, decimal forms, repeating decimals as sum of infinite geometric sequences. So that is the technique. Okay, we can repeat a little bit just to revise what we have done. Okay, we have started here the sum of an infinite geometric sequence. The sum of an infinite geometric sequence. So let's take the formula. Sn is equal to a1 minus a1 r power n over 1 minus r. And rewrite the right hand side by applying the property. So this is the property. What is the property? If a minus b over c is equal to a over c minus b over c. So it means that this can be written as the separate sums. And then it means this can be written as a1 over 1 minus r minus a1 r power n over 1 minus r. Now, if we apply the condition that common ratio is less than 1, it means, or we can say that common ratio lies between minus 1 and 1. What will happen? Suppose that common ratio is 1 by 2. So if the first term is 1 by 2, then the second term will be r square 1 by 4, 1 by 8, 1 by 16. So if you observe, the coming terms are getting lesser than the existing term. So we can say that actually this sequence is approaching to 0 and very close to 0. It means we can neglect this second term. If we neglect this second term or remove, we have the formula Sn is equal to a1 over 1 minus r. Okay, so then now we apply this formula. Find the sum of the infinite geometric sequence. This is an geometric sequence, and the first term is 1, common ratio is 1 by 2, and apply the formula first term over 1 minus r. We will get the sum of all these terms equal to 2. So we can observe that the first term will be 1, second will be 1 plus half, third will be this one, then fourth, and then fifth. So if r greater than 1, we have observed that the sum is increasing, not decreasing. So just observe that if r is less than 1, the next term is decreasing, minimizing. But if r is greater than 1 or less than minus 1, okay, the both have a problems. So if r is greater than 1, if you observe, the next term is increasing, not decreasing, increasing. So this is the second term 9, third 27, then 81, then 22, 43. Similarly, if r is less than minus 1, so again the terms are fluctuating. First is one says positive and the other way is negative. So it is oscillating term series. Oscillating mean, so once you have positive sign and next you have a negative sign. So if r is equal to 1, then Sn is equal to Na1. We can write like this one. And as n increases without bound, Sn also increase without bound. So if r is equal to minus 1, then Sn will be either a1 or 0. Therefore, we can say that the sum of infinite geometric sequence does not exist if common ratio is greater than or equal to 1. Repeating decimals as sums of infinite geometric sequence. So now we can write repeating decimals as sums of infinite geometric sequence. How we can write? For example, if we have a 2.23, we can write as 223 over 100. If we have 0.147, we can write as 147 over 1000. Okay, so this is the way to convert these decimals. Okay, so then how we can write these repeating decimals as the sum of infinite geometric sequence. For example, change 0.14 bar to a over b form where a and b are integers and b is not equal to 0. The repeating decimal 0.14 bar can be written as the indicated sum of an infinite geometric sequence with first term 0.14 and common ratio 0.01. So 0.14, 0.0014 plus 0.4 times 0, 14 plus so on. So using this formula, S infinite is equal to a1 over 1 minus r. We obtain S infinite is equal to 0.14 over 1 minus 0.01 is equal to 0.14 over 0.99 is equal to 14 over 99. Thus 0.14 bar can be written as 14 over 99. Similarly, repeating decimals 0.56 bar to A over B form, where A and B are integers and B is not equal to 0, can be written as repeating decimal 0.56 bar can be written 0.5 plus 0.06 plus 0.006 plus 3 times 0.6 plus so on, where 0.06 plus this one is the indicated sum of the infinite geometric sequence, with A1 is equal to 0.06 plus R is equal to 0.1. Therefore, S infinite is equal to 0.06 over 1 minus 0.1 is equal to 0.06 over 0.9 is equal to 6 over 90 equal to 1 over 15. Now we can add 0.5 and 1 over 15. So 0.56 bar is equal to 0.5 plus so on 17 over 30.